Hello, hello. Am I audible?
Yes, madam.
Oh, okay, and my screen is also visible.
Yes.
Okay, so we'll start. We'll start after two minutes.
Ma'am, in the CE edge, what is the weight?
Uh, okay. Yeah. Wait. Okay. So yeah, it is 5. Good evening, everyone. I welcome you to the seventh problem solving session of NPTEL course Graph Theory. So today in the lectures, the in week 7, what was discussed was problems on network, finding maximal flow and minimum cut. So today we'll be discussing that only. So as always, first we'll recall the concepts and then we'll look at some question. So first of all, the first concept is so first of all, the first concept is of a network. Okay. So if you don't have any questions, then you can mute yourself. And if you when you have question, you can unmute yourself. Okay. So what is a network? So till now, till the last lectures, what we were working with simple graphs and non-directed graphs. That is that all the edges did not have any direction, but in this lecture, when we are calling a network, so this network is a special kind of a graph. First, it is a special kind of a graph. First of all, it is a directed graph. That is, every edge has some direction. Secondly, it has two distinguished vertices, which is source and sink. So source vertex is denoted as S, sink vertex is denoted as T. So these are two special vertices in the sense that if we are talking about a source vertex, there is all the edges are going out of S. And when we are talking about a sink vertex, as the name suggests, all the edges are going into T. So there is no edge going out of T. So that's why the name source and sink. And every directed edge every directed edge has capacity. So if a graph has these three properties, then such a graph is called a network. So now once we have a network, the most common problem is basically to find the flow or maximum flow. So what is a flow? So my voice is audible to everyone, right?
Yes, yes.
Okay. So what is a flow? Flow is a so now flow now we are given a network. The flow refers to any function which is assigning real value to each directed edge uv, and we have these following rules. First rule is the capacity rule, which says that flow if so we are assigning some real value to each directed edge. Suppose uv is an directed edge, then the first is that flow assigned to the edge uv should be less than equal to the capacity of uv. So we cannot assign a flow which is greater than equal to capacity. And secondly, we have conservation law, which says that if we take any vertex which is not a source vertex or a sink vertex, flow which is coming, suppose that vertex is v, flow which is coming into v, by that we mean flow into v by means that we look at all the edges which are coming, all the edges which are ending at v, and then we look at the flow at those, so that is flow into v. And similarly we also have flow out of v, the all the edges which are going out of v, that is the edge whose initial vertex is v. So this flow into v should be equal to flow out of v. So if any real function is satisfying these two rules, then we say it is a flow function. So for example, so you can see that the graph on left is a network. Why is it a network? It is a directed graph, all the edges have some direction. Secondly, it has a source vertex and a sink vertex. And thirdly, all the edges have some capacity. So all the properties of networks are satisfied. And now the claim is that the diagram on right is a flow diagram. So to say that, so diagram on the right is determining a flow. So when we are writing numbers, uh, okay, when we are writing numbers like 2/3, so the since flow is less than equal to capacity, first term is the flow value of the edge and second term is the capacity. So to say that this function f, that is the values which are appearing on the first thing, is a flow, we have to check these two properties. So are these two properties satisfied? First of all, you can see what is the first property. First property is that flow should be less than equal to capacity. So in each of the things, 2 is less than equal to 3, 2 is less than equal to 2, 1 is less than equal to 1, 5 is less than equal to 5, 4 is less than equal to 4, 5, and all. So in all the edges you can see that first rule is satisfied, that is capacity rule is satisfied. So what about the conservation law? Do you think a conservation law is satisfied in this? Hello. So do you think conservation law is satisfied?
Yes, madam. Yes.
So to see that conservation law is satisfied, first of all we have to check for each vertex other than source and sink. So basically not other than S and T. So if we look at vertex A, what is the inflow in A? So for vertex
Two.
2,
Two.
because there is just one edge which is coming into A, and similarly flow out of A is also 2. So for A, this is right. For what about D? What is the inflow in D?
Two, madam. Two.
2. There are two edges, but the this edge is contributing 0, so 2. And outflow is also 2, because we have dt and de. So for D also, this conservation law is satisfied, and similarly for B, 0, 0. For C also it is satisfied, because for C we have to look at FSC, and there it is FCE. So 4 is equal to 4. So for C is also it satisfied, and for E, is it satisfied for E? So for E we see that inflow is basically FDE plus FCE, which is 4 plus 1, and outflow is also 5. So which is just ET, which is 5. So we see that A and B property is satisfied, therefore it is indeed a flow. Now once we know what is flow, then what is the value given a flow that is a function from edges to R, satisfying those properties A and B. Total flow is basically, either we count flow out of source, that is all the vertices, all the uh, all the edges which are going out of S and calculate that flow, or flow into sync vertex. So in this above network, okay, so there, so in this above network, what is the value of flow? So in this above example, what is the value of flow?
5, ma'am. 5. Sorry,
5, 5,
6.
yeah, 6.
6, ma'am. 6.
6, because we have to count F SA plus FSB plus FSC, which is 2 plus 0 plus 4, which is 6. Okay. So, has everyone understood the definition of flow and the value of flow? Okay. So if we have this
Ma'am,
now,
but there is one more option where the value is 6, but the flows are different.
okay, yes, yes,
So the same value is 6, but flow rate is different, ma'am. Can I give you that?
yes. Okay, we'll check whether it is a flow. Yeah. What is your example? Yeah.
Ma'am, from S to A, it is 1.
Okay. 1 out of 3. Hmm.
S to B is 1.
Okay. Hmm.
And S to C is 4.
Okay. Yeah.
Similarly, A to B, D is 1.
Hmm.
B to D is 1. C to E is 4.
C2 is 4. Okay.
And similarly, E to T is 5.
E to T is 5.
5.
Okay.
And D to T is 1.
D to T is 1.
And D to E is also 1.
Okay. So if you are saying it is a flow, then we have, so first property is clearly satisfied. We have to check whether the second property is satisfied. That is the conservation law. So for A, it is fine. For D also, for D, is it fine? So flow into D is AD plus BD, which is 1 plus 1, and going out is also DT plus DE, which is 1 and 1. So for D also it is fine. For B it is fine because it's 1 1. For C also it is fine. Yeah. And for E also it is fine. Yes, yes, it is also an example of flow. Yes, you are right.
But man, out of two, which is better, man?
uh, so since both of them have same value, so so there's, as in, like, you cannot say which one is better. So we are mostly interested in the flow with maximum flow, but since both of them are having value 6, so either of them is fine. Like, in terms of flow, you can't compare. Okay.
But ma'am, if you see mathematically 0 by 1 or 0 by 1,
Hmm.
that means in that edge is not directed edge is not satisfied. So logically, if you see the flow in which all the edges are utilized, that is the best one for as far as optimization is concerned. If we have two options, then only this will happen.
Hmm. No, yeah, yeah. So if, see, that depends on what you are like looking for. So if you are just looking for, yes, it is better in that sense that, okay, so in so in the second flow there are we have some edges in which we are not traveling, in a sense. Yes,
Yes, ma'am. Yes, yes,
but still we can't say it is like, so if you are looking for that particular property, then in that sense obviously it is better, but in general you can't say it is better, right? So, to say
yes,
it is
yes,
better,
yes.
you have to define what we mean by better.
Better means utilization of all your resources. That
Yes,
is the
if you are saying that, yes, then in this sense, that is fine. Yeah. Okay. Okay. So, so now if the definition of flow is fine, then we can go to the first question. So we have so it is not an network in the sense that the edges are not directed, but so in the right, so this is these are the capacity. In the diagram on the left we are given the capacity of each edge, and on the second diagram we are given the flow. Now in this, what we have to do is that we have to give directions to each edge, the edges in which directions are
ma'am.
missing.
In previous question, we have not calculated minimum cut.
No, so
The-
so we haven't, I haven't like, so I'll get back to it. So for like for first topic is just the flow, we'll be calculating minimum cut. Yes.
Okay, ma'am. Okay.
Yeah. Okay, so the first question is this. So basically in on the left there is this, we have capacity and this is flow. So you can see that these edges don't have direction, so you have to give these edges direction such that conservation law is satisfied. And this is saying that flow value of 28 is given, so that means s. So if we are saying S and T is a source vertex, so what is the direction of SA, SC and SE?
All are going out, ma'am.
Yes, all are going out. Yes. So first of all, the directions for SA and C are this. So now what about the sync vertex? So what are the edges going into sync vertex?
All are going into the sink.
So basically B, so we know the direction for BT, DT and FT. Okay. Now the directions for what all directions are left? We have to give direction for AB vertex, sorry, AB, AD, CD, CF and EF. So we have to give directions to these middle edges. So now first, so what edge, what direction is obvious?
A to B and B to T.
A to B and B to T. B to T we have already
Yes.
given 9. Yes. So you are saying A to B should also be 9. This is A to B direction, right?
Yes. Yes.
Okay. So yeah, because in so in this you see, so if we are applying conservation law on B, so the edges which are there are AB, BD and BT. So outflow from B is 9. So inflow should also be 9. And this is the only possible case. So AB direction should be A to B. Okay. So now we are done with AB. Okay. So now flow into A is 10. So can we give any so what will be the direction for AD?
A to D.
A to D, because if we have to look at the conservation law for A, flow into A is 10 and out should also be 10. So 9 is contributed by AB, we also need 1. So the direction of AD should also be A to D. Okay. Now, so we are AB, AD. Okay. So any other? So what about if we want to apply conservation law on C? Or first of all, if we want to apply it on D? because mostly all the directions for D are given. So let's apply it on D first. So what is inflow in D?
It is 1.
Up till now it is 1, and outflow is 9. Outflow is
9.
9. So we also need a 8. So so it should come from
C to D.
C to D. So we get the direction for C to D also. Now, what about the leftover edges? What is the direction for C, F and E, F? So for if we apply
F
conservation
to
law,
C. F to C, ma'am.
yeah, F to C. Why F to C?
Because C to D is 8.
C to D is
So
8. Yeah.
so 4 is both 4 should go inside.
Yes. Because outflow is 8 and till now inflow is only 4. So there should be more inflow of 4 units, which will come from F to C. And the last, what should be the direction of E to F? Of edge EF? What should be the direction of edge EF?
A to F.
E to F. E to F, because in inflow is 14. So outflow should also be 14. So it should be E to F. So is this question clear to everyone?
Yes, yes.
Okay. So now this was flow. The second concept is of second concept is of cut. So we have studied cut in many of these previous lectures also. So what do we mean by a vertex cut or cut? Is basically we are partitioning our set of vertices into two sets, S and S complements, and edges in this cut have one endpoint in S and other endpoint in S bar. And in in our in our okay, okay, so wait, something happened. So yeah, st cut is basically a cut in which source vertex is in S and source vertex is in S and sink vertex is in S complement. So now if we are given this directed graph, given this network, an example of cut can be, we look at SABC in S and S bar we take it to be DET. So this is partitioning our set of vertices into two, hence it is a cut. Now once we have a cut, so for network we also have notion for capacity of a cut and a flow of a cut. So what do we mean by a capacity of cut? So we look at all the edges, we look at all the directed edges U to V, where U is in S and V is in S bar. So we are looking from edges going from S to S bar, and we sum up the capacities, and we sum up these capacity and of those edges, and the resultant amount is the capacity of cut. So in this example, if this is the cut, so we have to look at all the edges whose initial vertex is in S and the final vertex is in S bar. So what all edges are there of that type? What all edges are there? So we can see AD, BD and CE are the only three edges whose initial vertex is in S and final vertex is in S bar. So we cannot take an edge of type SB because both the vertices of this are in uh, both the vertices are in S. And also uh, basically we have to consider all the edges whose first vertex is in S and second vertex is in S bar. We are not allowed to take this kind of thing also, some edge which are going from S bar to S. So when we are counting capacity, so the definition says that we have to look for all those edges whose first vertex is in S and initial vertex is in S and final vertex is in S bar. So in this example we see that the edges of those type are AD, BD and CE. So capacity is 2 plus 1 plus 5, which is 8. Now once we are given capacity, and if we are also in additionally given flow, so what will be the net flow of the cut? So in this, when we are looking at net flow of cut, we are interested in capacity. We were only interested in the edges which were going out of S to S bar, but when we are computing net flow, we are looking at all the edges. So we are also looking at the flow out of S, and we are also looking at flow into S. So net flow is basically flow out of S, that is we look at all the edges which are going from S to S bar, and we add those, and then we subtract the flow of edges which are going from S bar to S. So basically net flow is flow out of S minus flow into S. So now we have this example of a flow, and first our vertex cut is SABC, yellow vertices. So what will be the flow in this case? So what will be the flow in this case? Does everyone understand the question?
No, ma'am. Please repeat again, ma'am.
Okay. So so we are given so S1 and S bar is a cut. That means S1 has vertices SABC and S1 bar, which is the S1 complement, which has the leftover vertices, which is DET. Now we have to compute net flow of this cut. So what do we mean by net flow of this cut? First we'll look at all the edges. First we look at all the edges which are going from S to S bar. So basically first, so what are the edges whose initial vertex is in S and final vertex is in S1, whose initial vertex is in S1 and final vertex is in S1 bar? So what all edges are there?
A to D
A to D,
and
B
B,
to
B to D and
and C
C
to
to E.
E. So yeah, so
So
these
that
are the, so
total
this
flow
is,
is 6.
so this is flow out of S. So we'll add this basically FAD plus FBD plus FCE, and we subtract flow into S. So is there any edge which is going from S1 bar to S1? Do we have any edge like that?
No.
No. So we have nothing. So we'll subtract nothing. So we'll see that it is 2 plus 0 plus 4 minus 0, which is 6. Now if now S2 is SAB, so now what is net flow? So first of all, what is outflow? When S2 is SAB, so what is S2 bar? We are looking at complement. So all the vertices other than SAB, which are C, D, E, T. So net flow is outflow minus flow out of S minus flow into S. So flow out of S2 is basically all those edges which are going from S2 to S2 bar. So what all edges are those? Now S2 is the orange vertices, and S2 bar is this pink. So what is the flow out of S? So basic flow out of S, Flow out of S2.
S2 is C, D, E, C, D, and E, T, na ma'am?
No, S2 is SAB.
S, A, B. Why ma'am S, A, B? Why not C also?
No, no, I'm taking this example. So I have
Okay,
written
okay,
S2 is SAB.
okay.
So what
So
is,
out is only two ma'am.
why?
S, A, B. So out, so only there is a flow from S to A ma'am.
No, no. So flow from S, we have to look from S2 to S2 bar. So first vertex is in S2, other vertex is in S2 bar. Flow out of S2 will be that. So it will be F, SC and FAD. So when we are saying flow out of S, that means initial vertex is in S2, flow out of S2, then initial vertex is in S2 and final vertex is in S2 bar. Okay.
Yes, yes.
S2 is equal to SAB. So this is flow out of S is FSC plus FAD. But what is flow into S? If you have to look flow into S2, that will be uh, initial vertex is in S2 bar and final vertex is in S2. So do we have any edge going from S2 bar to S2? If S2 is SAB and S2 bar is CDET.
No ma'am. No, no,
No,
no, nothing.
no. So it is FSC plus FAD. So this is also 6. So does everyone understand the definition of net flow of a cut? So basically, if S bar is a cut, net flow of a cut is we are computing flow out of S minus flow into S. Flow out by flow out of S we mean that we are looking at all those edges which are going from S to S bar. So first vertex is in S, second vertex is in the S bar. And if we are looking at flow into S, then we are looking at S bar to S. So this is net flow. Now we have some lemmas on capacity and net flow. So if G is a network and SS bar is a ST cut. By ST cut we means that source vertex is in S and F is a flow, then we can say that net flow is always equal to the flow value. So in this example, you can see that flow of cut is coming out to be 6 for both the cases and total value of flow also is also 6. So lemma 1 says that flow value will be equal to always equal to the net flow. Second lemma is that any flow value will be less than equal to the capacity of a cut. And thirdly, we have that if flow value is equal to capacity of some cut, then F is max flow and that this cut is the minimum cut. So by minimum cut, we means that cut with minimum capacity. So we look at the graph, similar graph. So suppose this is the example. Let's see if all these three properties are holding. So in this first cut is SB. So first of all, what is the capacity of this cut? What is the capacity of this cut?
Two ma'am.
Okay, you have to say why. So how are you calculating the capacity? Yes. How are you calculating the capacity? So Anupam, you said it is 2. Why did you say it is 2?
Ma'am, I am encircling A and B only in one circle, and rest all complement is A, T, and C.
No, no. So see,
So,
if in our first part S is given to be SB and it is a ST cut, so source vertex should be in S. So first is SB, our S is SB. So this is our cut.
okay, sorry, then I am wrong.
Yes, this is the cut. This is our cut. SB. So we have to look. So capacity, for capacity we have to look for edges which are going from S to S bar. So what all edges are going from S to S bar? Capital S to capital S bar. What all edges are going?
S to A and B to C. B to C.
S to A, B to C. Any other?
And B to A is also going, ma'am.
Yes. So this is CSA plus CBA and plus CBC. So we see it is 3, right? 1 plus 1 plus 1, it is 3. What about flow? Net flow. So we'll first of all take all these edges which are going out of S, which is same as FSA plus FBA plus FBC. But when we are computing net flow, we also have to look for edges which are going like this, basically from S bar to S. So we also have to look for those edges. So are there any edges which are going from S bar to S?
No.
No. No, there is no such edge. So, so, okay. Yes. So there is no such edge like this. So we see in this flow is coming out to equal to the, okay, so the capacity is 4. So this is for first one, capacity was 2. So this is 2 plus 1 which is 4. So when we are looking at capacity, we are looking at this number. So capacity is 4 and flow is 3. So we see that net flow of cut is coming out to be less than equal to capacity. So is the first example clear to everyone?
Yes, ma'am.
Now what about the second part?
Yes.
So we see that first lemma is satisfied. That second lemma is satisfied that flow is less than equal to capacity. Flow is less than equal to capacity. First lemma was that flow should be equal to the net flow. Is the first lemma also satisfied? So we see that net flow of cut is coming out to be 3. And what is the value of flow in this? It is also 3. So first lemma is also satisfied. And second lemma is also satisfied. Now if we take our cut to be SAB. So S has SAB and so this is the cut now. Now what is the capacity of this cut?
So there is a edge from A to T and B to C. The capacity
Capacity
is
three.
C of AT plus C of BC.
Yes,
That
which
is
is
2 plus 1, 3.
2 plus
Three.
1, 3. And flow will also be
3.
FAT plus FBC. And there is no edge going from S bar to S. If there was an edge going
Yes.
from S bar to S, then we'll subtract it. But since there is no edge going, so we see it is coming out to be 3. So in this we see that flow is coming out to be flow is coming out to be equal to the capacity. So from lemma 3 we can directly conclude that if flow is coming out to be capacity, that this is the maximum flow and this cut is also the minimum cut. Okay, so has everyone understood the definition of capacity of a cut and net flow of cut? Any doubts in the definition? Okay, so now this is a question. So we have this network below, we have to find the capacity and also the net flow of this cut. So S is basically SCEDF. So this is the cut now. So this is the cut. So as our example before, this question is similar only. Okay, not. So S has basically S, C, D, E, F. So what is S bar? S bar is complement. So A, B, T. So now we have to find the capacity of the cut. So what is the capacity of this cut? So we have to look at all the edges which are going from S to S bar. So what is the capacity? So we are looking at, so the edges which are going are C, S,
Yes,
A,
SCA plus C of dt d comma t,
T, comma T. Yes.
and capacity of F comma t.
Capacity of F, comma T. Okay.
T. It
Any
is
other
10 plus
edge?
10 plus 10.
Any other edge? So capacity of this cut is 30. What about flow? What about flow?
This 10, sorry, f of x comma a,
F of S A plus.
f of d comma t, and plus f of f comma t,
And is there any edge which is going from S bar to S?
ad. There is
AD.
an edge from a.
AD. So we have to subtract that. So what is the now the value? FSA is 10. FDT is also 10. FFT is 10, but FAD is minus 10. So
Minus
this
10.
is 20. So this is the capacity and net flow of the cut. And in this also you can see that net flow is coming out to be 20. Net flow is coming out to be 20, which is equal to the flow value. Flow value of this cut, total flow value of this network is also 20, because the flow going out of S is SA plus SE, which is 20. So net flow is coming equal to the value of flow. And secondly, that flow value, net flow value is less than equal to the capacity of cut. Okay, so these two are
But ma'am, this is not the minimum cut, na? Because
yes,
because it
yes, this
minimum
is
it is
not the
not the
minimum
minimum.
cut. To say it is a minimum cut, then if it was a minimum cut, then flow value should come out to be if it was a minimum cut, then capacity should come out to be the equal of uh, capacity
Equal
of
to the
cut
flow.
flow.
Yes. In this, ma'am, which is that set can we calculate or
So yes, so in later question we'll be calculating the maximum flow for this. Yes. So first of all, I'll let you know how to compute the maximum flow and minimum cut. Then we'll solve these question. Now we have understood what is flow. Now we have understood what is flow and what is the capacity and net flow of the cut. Now the next question is, if we are given a network, how to find the maximum flow. So there's an algorithm to find the maximum flow. So for that algorithm, first we require, given a flow, first we should be able to calculate the residual flow. So what is a residual flow? If we are given a network G and which has flow F, then residual G is also a directed graph which has vertices same as G, but and for each directed edge UV in this new graph GF there will be one or two edges. So first of all, given a network G and a flow F, we are constructing a residual flow. So residual flow is a directed graph. So if it is a directed graph, and if we are constructing a directed graph, we should be knowing what are the vertices of that graph and what are the edges of this graph. So vertices of residual flow is same as the vertices of the network, and edges, now we have to construct the edges of that graph. So we look at each edge in G, and we look at each edge, directed edge in G, and corresponding to that we construct one or two edges in the residual flow. So first of all, if flow value is strictly less than capacity value, then we'll construct a forward edge in the residual flow, that is UV is a directed edge in G, and if flow value of UV is less than CUV, then we'll construct a forward edge with UV, and the capacity will and the weight of that edge will be the difference, that is CUV minus FUV. And secondly, if FUV is greater than 0, we'll also construct a backward edge, that is a direction, that is if UV was an earlier edge, we'll construct VU, and the weight of that edge will be the weight of the flow. So suppose this is an example. There can be three type of cases. Suppose this is an initial network given G, and there is an edge like UV which has flow 3 and capacity 5. So the first condition is satisfied for this edge, that is flow is strictly less than capacity. Therefore we'll have a in the residual flow we'll have a graph. In the residual flow we'll have a edge in the same direction UV, and weight of that edge will be the difference, which is 5 minus 3, which is 2. And in this, second property is also satisfied, that is flow is strictly greater than 0. Flow value is 3, it is strictly greater than 0. Therefore we'll also have a backward edge, that is a edge in the reverse direction, and the weight of that edge will be equal to the flow value. So this is the first kind of scenario. Second scenario is when flow value equal to the capacity. So in this you see that first property is not satisfied, so there will be no forward edge in the residual graph. But second property is satisfied, that flow value is strictly greater than 0, so there is only a backward edge. And third case is when flow value is 0 and capacity is 5. So first property is satisfied, that flow value is strictly less than capacity, so we'll have a forward edge with weight 5 minus 0. But second property is not satisfied, that flow value is strictly greater than 0, so there will be no backward edge. So this is the three kind of scenarios which can happen. So why we are given a flow, first we are considering constructing residual flow. Now with the help of residual flow we'll be able to tell whether the given flow is maximal or not. Hence we are constructing this residual flow. Okay, and we are constructing it in this manner. So let's try it with an example. Suppose this is my graph. Suppose this is my network G, and now I am constructing GF. So first I'm considering this edge SA. So, so how many in the residual graph? How many edges will be there?
Forward edge, because it is greater than 0,
It
S to A.
S to A flow. There will be only forward edge because flow is strictly less than capacity, right?
Yes, ma'am.
Yes. Will there be a backward edge?
No, since it is not greater than 0,
Greater than 0. So there won't be any backward edge. So we see that in
backward.
residual graph there is just SA. Now similarly if we look at AD, so all these edges which have flow 0, there will be, so all the edges which have flow 0 in the residual graph there will be only forward edge. So for SA, AD, for
Yes,
for
A,
SA,
AD,
AD,
CB,
CB and BT. There will only be a
BT.
forward edge because second property is not satisfied. So in this we can see that flow value is strictly less than capacity. So we have a forward edge, but for backward edge we need a positive value of flow. So there is only this. Now second type is, now if we look at this edge SC, if we look at edge SC and dt, in this first property is not satisfied, that capacity in this flow value is equal to the capacity value, that is flow value is not strictly less than capacity, so there will only be a backward edge, there will be no forward edge in the residual graph. Is it fine? Is it fine?
No, ma'am. Another property, I think.
Yes. So, so no, so I'm so for there will be no forward edge for
Only
SC and
backward edges.
DT. For so the so for so we have this property that if flow value is strictly less than capacity, then we have a forward edge. But in these purple edges, we see that flow value is equal to capacity. So
There will not be any forward edges.
there is no forward
Okay.
edge. But flow value is strictly positive, which is 10 and 10. So there will be a backward edge of 10 weight. And the third type of edge is basically this CD. In this, flow value is strictly less than capacity. So there is a forward edge with the difference, which is 13 minus 10, 3. And flow value is also positive, which is 10. So there will be a backward edge of weight 10. So this is an important concept. So does everyone understand, given a network G and a given a network G and residual flow, given a network G and a flow, how to compute the residual flow? Any doubts?
No, ma'am. So shall I give the ma'am augmenting path in this? Shall I try?
Yes. Okay. So one second, I'll ask. So is everyone clear with how to compute the how to compute the residual flow?
Yes.
Yes, ma'am. Yes, ma'am.
Yes. Okay. So now, once we have residual flow, then we need a augmenting path. So what is an augmenting path? Augmenting path is by definition a ST path in the residual flow. That is a path starting at S, ending at T in GF. So does this graph has any residue? Does this graph has an augmenting path? Does GF has an augmenting path?
No, ma'am.
Okay, so you are saying there is no. So in G, you have to consider in GF, not G. That's why we are constructing residual flow. So can anyone? There is a augmenting path in this graph. Find it.
Okay, ma'am. Then SA,
Okay. S
A D
S A A D
B D D C
D C
C B
C B
and B T.
B T. So this is the augmenting path. So why it is an augment? It is starting as S and ending at T. And since we are in a directed graph, we have to take in we have to look at the directions, and we see that we have these right directions. So we have an augmenting path. So now
But
the
ma'am, I have one doubt, ma'am.
yes.
So while going from D to C,
Hmm.
we have a direction from C to D. If the capacity of the residual network is three,
Hmm. Yes.
so now we are going against the residual network. If we, that the three, if you say black and orange
Hmm. Hmm.
lines,
Yes.
so we are okay for S to A 4 is okay,
Hmm.
A to B 4 is okay,
Yes.
but from D to C we are going against the three direction. That is the doubt, man. That is why I initially say no.
So
But because there is a residual network of three, so I give him this path.
yes. So basically, yeah. So see, this is. So I'm just for the, so this is an edge in this graph, right? So this graph in G now GF. So now GF is construct. So basically, the purpose of G is constructing residual flow is that. So we'll see that if a residual flow has an augmenting path, then we can construct a new flow with a higher value. So in this we are also considering a back in this we are also considering backward edges, in the sense that it might be possible the original flow that we have assigned, if we decrease flow from some edge and increase in some other edge, then we are getting a higher flow. Therefore we are also considering backward directions also. Our aim is to find our aim is to find flow which has maximum value. So given a flow, it might be possible that to get a better flow, we have to reduce a flow in some edge and increase in some other. So this backward edges kind of are coming due to that reason. So these backward edges are also important. So in this, now when I am saying augmenting path, by definition augmenting path is a path from S to T, and it can so basically we can take any of the edges, either the black or orange edges.
Okay, for that is a confusion. So now that means
Huh.
if I have to calculate augmenting path, I
Yes.
can go via black also and via
Orange
orange
also.
also.
Yes,
Yes, yes,
because
then
both
it is
edges
okay.
are part of the graph.
Yes,
Yes.
yes, then it is okay. And then the capacity of the latest, like the minimum is three, so we can increase flow by three.
Increase no, yes, we'll increase flow by 3. Yes. So now the next concept is, if we are given an augmenting path, so we see that this is our augmenting path. Now we have to look at the path capacity. So in this GF only, we'll look at all the edges and all the edges in that path. So we have to look at the so path capacity is basically minimum of the capacity of the edges in this path. So in this path, what are the edges? SA, AD, SA, AD, DC, CB, and BF. So what is the capacity of SA in this GF? What is the weight here? It is 4. For AD it is also 4. For DC it is 10. For DC it is 10. For CB it is 4. For BT it is 4. So what is the minimum value here? Minimum value here is 4, not 3.
Now, ma'am, we have to take the capacity of a residual network. So residual network, we have four, four, three, four, four. So that is
Yes.
why I said three.
No, no. Backward edge has weight 10.
Backward is 10, but now to increase the flow, I think, ma'am, I may be wrong.
No, no.
So
So see, we are looking at GF. We are so no. This is the definition. Path capacity. We look at the weights in the residual network. So this is the residual flow. So in this minimum is 4. We don't look at the original one. We look at the GF. So in this the minimum. So SA has weight 4. AD has weight 4. DC has weight 10. CB has weight 4 and BT has weight 4. In this minimum of those is 4. So the path capacity is 4.
ma'am, why we DC we have 3 and 10 both, na ma'am. So minimum is
No,
3.
no. DC is 10, CD is 3. We are looking at a directed graph. So we are taking the direction DC. Direction
Okay,
DC has weight 10.
okay, understood, understood.
Right? So does everyone understand what is the definition of path capacity also? So now if we have a so basically what we have, this was G, then we constructed a residual flow. This residual flow also had an augmenting path of capacity 4. So once we have an augmenting path of capacity 4, once we have some augmenting path, then we can construct a new flow using that augmenting path. Okay, so how do we do? So this was the original flow. Now we had an augmenting path was SA, AD, DC, CB, BT. Augmenting path is this in GF. So this is my augmenting path in GF. So this has weight 4, AD has weight 4, DC has weight 10, CD has 4 and BT is 4. Now since path capacity is 4, so to get the new flow, what will we do? So the path, if it has a same direction as in the residue, as so if the if the path in the residual, if the edge in the augmenting path has same direction as in the our original network, we'll add path capacity to that edge, and if it is in the reverse direction, then we'll subtract that path capacity. So that's why we were making it with a different color to keep track it. So now SA has same as SA was a forward edge, therefore the new flow, in the new flow we'll add the path capacity, which is 4. So this will be 4 by 4. The next edge is AD. AD is also a forward edge in the residual network. So the new flow will add 4 to the original flow. Original flow was 0, so 0 plus path capacity, which is 4. So this will be 4. Now DC was a backward edge. Therefore, we'll subtract the path capacity from DC. So it was originally 10. Then we'll subtract the path capacity, which is 4. So now this will become 6, 13. 6 by 13. Then we have the next edge is CB. So what will be the new flow for CB? Is it a forward edge or a backward edge?
Forward,
So what will be the new flow for CB?
4 by 4.
4 by 4. And for BT, is
4
BT
by
a
4.
forward edge? So this is also 4 by 4. So now initially the flow value was 10. Now we are getting a new flow value of 10 plus path capacity, which is 14. So this was the point. This is the kind of algorithm. Given a flow, first we construct the residual flow. First we construct the residual flow, and if that residual flow has an augmenting path, that is a path from S source vertex to a sink vertex in the residual flow, then if it has an augmenting path, then it will have some path capacity, and if it has an augmenting path with path capacity k, then we can construct a new flow which will be which will be more k value. So initially flow value was 10, then we constructed a residual flow. We were able to construct an augmenting path which has path capacity 4. So using that augmenting path, we were able to increase our flow by 40, by 4, which the new flow is coming out to be 40. So this is how we find the maximum flow. So in my example, we were already starting with a flow, but in general, if we have to find the maximum flow, we can take the trivial flow, which is we can take all the flow value to be 0 and apply this algorithm and keep on applying this algorithm until we get to a residual flow in which there is no augmenting path. And if our residual, if for a given flow f, the residual flow will have no augmenting path, then we can claim that flow is the maximum flow. Is it clear?
Yes, ma'am. Yes.
So now let's see. So now let's see, is 14 the maximum flow for this? So what we have to see, if we have to check if 14 is the maximum flow, what should be the steps?
We should see for residual network
Yes,
first.
yes. So now for this new flow, now for this new flow, we'll construct a residual flow. So let for neatness, let's this is the new flow, 4 by 4, 4 by 4. This is 6 by 13. So help me in constructing the residual flow. So first of all, if we want to construct the residual flow, this is
Ma'am,
G.
in this there is no residual flow. Why? By looking we can see.
Yes, why? Yes, why?
Because ma'am, see, because S and T both are exhausted. We cannot increase any value from S.
Yes, you are right. So what? So if we see that, we'll only have backward edges going here, right? All the, so this will be 4, this will be 10. If we'll construct the residual flow, this will also be 4 and this will also 10. So what about AD? This is also exhausted, so this is a backward edge. This is also exhausted, this is a backward edge. And for CD, we'll have one backward edge 6 and one forward edge 7. So does this residual flow have a ST path? So we
No.
can see there is no edge going out of S. So this GF cannot have a residual path. So sorry, this GF cannot have a augmenting path. And if this has no augmenting path, then the flow is maximum. So is it clear to everyone why this flow is maximum?
Yes, ma'am.
Okay. And this is the algorithm only. How, if we are given a network, how to find the maximal flow? We start with flow 0 0, then we draw the residual network. Once we draw the residual network, then we find the augmenting path. After augmenting path, we construct the new flow. Then for new flow, we construct the residual flow. And we keep on doing that until we get a flow in whose residual flow has no augmenting path. If residual flow has no augmenting path, then we conclude that the output is the maximum flow. Now, so now we can see that maximum flow can be related with minimum cut also. So minimum cut was the cut with the minimum capacity. So this was the theorem which was discussed in class, that if the following three conditions are equivalent: that F is maximum flow, there is no augmenting path in the residual network, and thirdly, there exists a cut with net flow F. So these three are equivalent. That so lemma 3 was that if our flow is coming out to be the capacity of some cut, then that flow is maximum and capacity is minimum. But this theorem is saying that if a flow is maximum, then we can always find a minimum cut also. So so this was the question that we did. This was the question that we did. So now we know that this is the maximum flow. But how do we find the minimum cut from this maximum flow? So we look at all these. So in this case, it is very simple. So we look at all these vertices U such that there is a path from S to U in the residual flow. So basically, we are looking at all those vertices for which there is a path from S to U. So is there a path from S to A in this graph?
No.
So so we in this graph, is there is there in this graph, is there any vertex such that there is a path from S to V? No, because we can see that there is no edge going out of S, so there cannot be any path. So we, in this case, our S is just S. So if we take our minimum cut to be just S, that is S. If we take our cut to be S, S to be S, and S bar to be AC BDT, S bar to be A B C D T. So what is the capacity of this cut? What is the capacity of this cut? What is the
14.
14? Because we have to look at all the edges which are going from S to S bar. There are just two edges, which is CSA plus CSC, which is equal to 10 plus 4, 14. And what is the flow value of this cut? Flow value of this network, of this flow, basically, it is also 14. So we see that S bar is the minimum cut and F is the minimum flow. So basically, how to find a minimum cut from maximum flow? We look at all the vertices such, so if you, so basically, if you are given a maximum flow, how do we construct a minimum cut? First, we construct a residual flow, and then we look at all those vertices such that there is a path from S to that vertex. We collect all those vertices, and in this graph, that vertex is just S. Therefore, S is just S. So in other questions, we'll see that. So does everyone understand, given a maximum flow, how to find the minimum cut? Given a
Yeah.
maximum flow, how to find a minimum cut?
In this example,
Yes.
from C, capacity of x comma x bar is equal to 14. Okay, the flow is from, we have to see from augmenting path, S to S bar or S bar to S.
Flow of net flow,
Yes,
net flow, no, okay, so flow, value of flow is basically, what is the value of flow? It is basically flow going out of the source vertex. So in
from
the,
the
you have to take it from the original
from
graph,
the
not the
graph.
residual flow.
Graph. Okay.
This is the, so the max flow min cut theorem says that if we have a maximum flow, that is a flow with the maximum flow value, and flow value is the flow going out of the source vertex. Or we see that if we, instead of this, we were calculating flow going into sink vertex, then also it is 14. So that is the flow value. Was this your question?
Yes, ma'am. I was checking on the augmenting path
Yes.
from S bar to S only. There is a 14 flow. where you have S is equal to, you have given the set single
Yes,
S.
yes,
So S bar to S only it is 14. Flow is 14.
yes.
Um, so the just it I had a confusion. That's all.
Yes, yes, yes. Is your confusion clear or no?
Yes, ma'am. Yes, ma'am.
Okay. So this
So
graph, if we have to look for augmenting path, we look in the residual flow. And in the residual flow, there is no path from S to T. And since in the residual flow, there is no path from S to T, the given flow is the maximum flow. Okay. So now let's look at some questions. This is done. This is done. Okay. So this is the question. So first question is we have to find the residual flow. And then we also have to look at the augmenting path. So, okay. Sorry. Okay. I wanted to. Okay. So first we have to find the residual flow. So what are the vertices of residual flow? All those vertices which are of the network. S, A, B, C, D, T. And then we have E, and then we have F. Okay. So this is this flow. Now help me in constructing the residual flow. So what all edges should be there between S and A? Forward, backward, and what direction?
Backward direction 10, ma'am.
Backward direction 10, because only one, because capacity flow is positive, but it is flow is equal to capacity, therefore there is only backward edge with 10. What about SC? What about SNC?
Forward 5.
Forward 5. Is there any backward edge?
No, ma'am.
Because flow is 0. Flow is, if flow there's a backward edge only if flow is positive. What about SNE?
5 forward and backward 10.
Yes, 5 forward, because we are looking at the difference. 15 minus 10 is 5, and backward is the flow value, which is 10. Okay. Now, what about AB? A and B?
Forward 9. Is it 9, ma'am?
No, it is 0. This is 0.
Okay, so capacity is 9.
Yes,
So forward is 9, ma'am.
forward is 9. What about AC? So all the values which have 0 flow, there will only be a forward direction. So
5.
AC, CD, and FC. So this is 4, 8, 6. What about AD? A and D?
A and D is 5 is forward and 10 is backward.
Yes. So is it clear to everyone how we are constructing the residual flow, or are there any doubts? Okay. What about BT?
Forward 10, ma'am.
Yes.
Reverse
There is
0.
no reverse. Forward 10. DT is backward. DT is backward 10. Similarly, TF also backward 10, because flow is non-negative, but both flow and capacity are equal, so there won't be any forward edge. And for DF, since the flow value is 0, therefore there won't be any backward edge, only forward edge, which is 15. So, and for EF, flow value is positive. Therefore, we will have a backward edge of flow value 10. And also we have like capacity is strictly greater than flow. So we also have a forward edge of 20. So this is the residual flow. So now the next question is we have to find the path capacity of the following augmenting path. So I'll highlight the augmenting path. Augmenting path is given to be SC, CD,
E A
DA,
S
AB and BT.
B T.
So what is the path capacity? So first of all, let's write down the weights. So we have S. What are the edges in this path? SC, CD, DA, AB and BT. So what is the weight of SC in the residual flow?
5.
Yeah, 5. For CD it is
8.
8. For DA it is 10
10.
because backward edge has weight 10. For AB it is 9. For BT it is 10. So what is the path capacity? So what is the path capacity? So path capacity is basically the
5, 5.
minimum of weights. So path capacity is 5. So so now we'll see the next question will be for the same question. So we have so this was the this was the original graph and this was the residual flow of the previous question. Now we have to construct the new flow and compute the new flow value of this augmenting path, of this augmenting path. So basically, so we are given, so in this question what we have done previously, so we were given a flow, then we computed the residual flow, then we also had a augmenting path. Now once we have an augmenting path and the path capacity is 5, so now the algorithm say that we should have a new flow, we should be able to construct a new flow with 5 more value. So now, so next question is to construct that new flow. So how to construct that new flow?
We have to take 5 in SC.
Yes. So basically now what we have to do is we'll have to change the flow. So all the edges which are up, all the edges which are appearing in the augmenting path will have a changed flow value. Rest of the edges will have the same thing. So now in this new graph, in this augmenting path, first edge is SC. So is if SC, and we see that SC as a forward edge. So what will be the new flow value for SC? What will be the new flow value for SC?
5 by 5.
5 by 5 because it is a forward edge. Now next edge in augmenting path is CD. So CD is also a forward edge. CD is also a forward edge. So what will be the new value of CD? So initially flow is 0. Now we'll add the path capacity to it. So it will become 5 by 8. Now what about DA? What about AD? What will be the new flow of AD? So the next edge in the augmenting path is DA. So that means we have to
Um,
change the weight of AD. flow of AD. So what is the new flow of AD?
15.
We have to reduce by 5, ma'am, forward.
Yes, yes, because it is a backward edge, then we'll subtract 5.
Oh, so
If it is a forward edge, then we add the path capacity. But if it is a backward edge in the augmenting path, we decrease the path capacity. So earlier it was 10, now it will be 10 minus
5.
5, which is 5. So is this point clear to everyone?
Yes.
So this
Yes,
is
ma'am.
the new flow. Okay. And now the next edge is AB. So AB is a forward edge. So what will be the new weight for AB? New flow for AB?
5 by
5 by
9.
9.
5 by 9. Because originally it is 0 and it is a forward edge. So we add the path capacity, which is 5 by 9. And for BT also it is a forward edge. So earlier the flow was 0. So now it will be 5 by 10. So this is the new flow. And you can see what is the flow value. What is the flow value?
25.
25. So earlier it was a flow of 20. Now when after a residual network we had an augmenting path with path capacity 5. So we were able to construct a new flow of a higher value. So now the next question. So is this question clear to everyone? Given an augmenting path, how to construct a new flow? So basically you have to keep that in mind. First of all, the flow of only those edges will be changed which are appearing in the augmenting path. And if the direction, and if it is a forward edge in a augmenting path, then we'll add the path capacity to the original flow. But if it is a backward edge, then we'll decrease the path capacity. So this is the rule. Is this question clear to everyone? Any doubts?
Yes, ma'am. But how can we prove that this is maximum? Can we go for one iteration? Again, we have to go by residual man,
Yes,
finding rest.
yes, this is the next question only. That is this flow maximum. So now to say that is this flow maximum, what we have to do is we'll again construct the residual flow. And if the residual flow will have an augmenting path, then this flow is not maximum, because if it has an augmenting path, then we can increase the flow. So let's see if this is the maximum flow or not. So so quickly help in computing the residual flow for this new flow. So first of all, this graph will have vertices same as the flow S, A, C, B, D, T, E, F. So okay. So what are the edges for SA?
Backward 10. SC is backward 5.
SC is
S
backward 5. Yes.
S E is forward 5, backward 10.
10. Okay. Is it clear to everyone? For SA, SC and SC how we are doing? So
Yes, ma'am.
yes. Now what about AB? What all edges will be there in AB?
Forward 4, backward 5.
Yes. Forward 4, backward 5. What about AC? Forward 4. And flow value is 0, so there won't be any backward. What about CD?
Forward 3,
For,
backward
forward 3,
backward
backward
uh,
5. Similarly for AD also we have backward 5, forward 10. For BT also we have two edges. Forward is 5, backward is also 5. For dt, since flow value is equal to the capacity, there is no forward edge. There will only be a backward edge. Sorry. There will only be a backward edge. For ft also there will be only a backward edge. For df, since flow value is strictly less than the capacity value but it is 0, there will only be a forward edge of the difference, which is 15. Lastly, what about cf and ef? So there are only two left. What about ef? How many edges will be there in ef?
Forward is 20 and backward is 10.
Yes, forward is 20, 30 minus 10 is 20, and backward is the flow value, which is 10. Okay. And is there any more left? Yes, there is this fc.
Forward is 6.
Yes. So
C
now
to
this,
F.
yes, so now this is the new gf.
Ma'am, direction is reverse. C to F is 6.
No, see, f to c only it is 6, right? Earlier it is f to c's. So this will
No, ma'am.
also be f to c.
No, no. You have shown direction from F to C is 0. Now capacity is 6. So it is other way around, na, ma'am, then.
No.
Initial graph, you see, F to C direction is 0. Now we have
So
to.
if it is, see, if it is f to c 0, then we 0 by 6. Then we have a forward edge by 6 minus 0, which is 6.
Yes, yes.
Okay. So now, okay, this is bit complicated, but do you think there is an augmenting path? So if it has an augmenting path, it will go from, it will it will be from s to t. So if this has an augmenting path, then that means that this is not a maximum flow. So is there an augmenting path? So augmenting, so let's try to see if it is if there is an augmenting path. So augmenting path will be a path from s to t. So everyone look at this graph and see if you can find an augmenting path.
Yes, ma'am.
Okay, so what is the path? Can you tell?
Now
Yes,
path is
E.
from S to E.
Wait, some he was answering first, right?
S E.
Yeah.
E F.
Yes, wait. I'll mark also. You are saying SE, yeah,
E F.
EF,
F C.
FC,
C D.
CD,
And D
DA,
A. A B.
AB, and BT. Yes,
B T.
correct. So there is an augmenting path. That means this flow is not maximum. So for first part is question, is this flow maximum? No. If not, find the maximum flow. So how will we do that? How will we find the maximum flow? So what should we do now?
See the capacities of the each path.
Yes. So this is an augmenting path. We'll find the path capacity of this augmenting path. So this augmenting path is SE, EF, FC, CD, DA, AB, and BT. SE has weight 5, EF has weight 20, FC has weight 5, CD has weight 3.
6. F C 6.
Yes, FC is 6. Thank you. Yes. FC is 6. FC is 6. CD is 3. DA is 5. AB is 4. And BT is 5. So what is the path capacity? So this is the augmenting path. P was this.
3.
S, E, F, C, D, A, B, T. And path capacity is 3.
3.
So So now if path capacity is 3, so what is the initial flow? F was initial flow is 10 plus 5. So initial flow is
25.
basically flow going out of S. So it will be FSA plus FSC plus FSE, which is 10 plus 5 plus 5, 10, 25. So now if path capacity is 3, what does that mean? If path capacity is 3, that means we should be able to find a new f prime which will have flow value 28. So help me in constructing that. So what we have to do is, if we have to find the new flow, we look at the original flow and all the edges which are appearing in the augmenting path will have a changed flow, but the edges which are not appearing in augmenting path will have the same flow. So this is, let's, okay, so let's find the new f prime. So let's find the new f prime. So first edge in the path is SE. So what will be the new flow for SE? What will be f prime SE? So path capacity is 3. So what is the new flow SE?
The forward is has to be
Forward edge will,
differenced by 3.
yes, we have to add or subtract.
Subtract 3 and add 3 in backward edge.
Yes. So we add the path capacity in the forward edge and subtract the path capacity in the backward edge. So SE is a forward edge and path capacity is 3. So this will be, so new SE will be 13 because it is an forward edge. And EF is also a forward edge. So what is, so the new path capacity here will be also 13. Similarly, for FC, also FC it will be 3. CD is also a forward edge. So for CD also it will be, we'll add 3. For CD also we'll add 3, 8 by 8. But DA is a backward edge. So if it is a backward edge, then we'll subtract 3. So this will be 5 minus 3, 2 by 15. And now AB is a forward edge and BT is a forward edge. So we'll add 3. 8 by 9 and 8 by 10. And rest all remain the same. So is this clear to everyone?
Yes, yes.
Okay. So now once we have this, then we have to then we have to see if it is the maximum flow or not. Okay, so this is the new flow to say that it is a, so this is f prime now. Now we'll repeat this procedure. We'll construct gf prime because the question say we have to find the maximum flow. So we'll have to repeat this procedure until we get a residual flow in which there is no augmenting path. So I'll just quickly make this also SC D. We'll create the residual flow. So we'll have the same vertices. So I am now this is f prime. Now I'm constructing residual flow with respect to this. So let's come. So for we see for this SA and AC, since since capacity is equal to flow, there will only be a backward edge 10, 5. But for SE, all those, like flow is also positive and flow is strictly less than capacity, so we'll have both the edges. Backward edge with the value uh, backward edge with value 13 and forward edge with value 2. For AB also we'll have both the things, forward edge with value 1, which is the difference, and backward edge with the flow value. For AC, just the forward edge. For CD, now it is exhausted, therefore only a backward edge because it is 8 by 8. For AD, it is 2 by 15. So both the rules are there. So we'll have both the edges. Forward edge with the difference, which is 13, and backward edge with the flow value. Okay. Now, uh, now for this, also we have a backward edge 8, forward edge 2. For this, just the backward edge, 10, 10. And for DAF, just the forward edge with value 15. For this, both forward and backward. A forward edge with the difference 13 minus 30 minus 13 is 17 and flow value is 13. And for CF also we'll have both the edges, forward is 3, backward is 3. So now we have constructed the augmenting graph. So the next step is, what is the next step? So we have constructed the residual graph. Now the next residual flow. Now the next step is to construct the augmenting path. If there is an augmenting path, then we'll say that
No,
we can
ma'am.
increase the flow. But if there is no augmenting path, then this is the maximum flow. So do you think
No,
there is an augmenting path?
no, ma'am. No augmenting path.
Uh, are you sure there is no augmenting path?
Yes, ma'am. There is no augmenting path.
Why? Because if we, so any augmenting path has to go from S to T. So there is only one possibly. We go from S to E. Then from E, there is only one possibility. We go from E to F. Then from F also there is just one possibility, F to C. But now after this we cannot go to any other vertex. Therefore we see that there is no path from S to T. No augmenting path in GF prime. And since there is no augmenting path, therefore F prime is maximal. So does everyone understand how to find the maximal flow?
Yes,
Any
ma'am. Yes.
doubts?
No, ma'am.
Okay. So there is one more part left of this question. So since this is a maximal flow, okay. Since this is maximal flow, we should be able to find the minimum cut. And for minimum cut, we have to look at, so minimum cut, we'll have to look at all those vertices U such that there is a path from S to U in GF prime in the residual flow. So what are all such vertices? This will form the minimum cut. So basically, if you all those vertices which has a path from S to this. So is there a path from S to S? Yes. Is there a path from S to E?
No, ma'am.
Is there a path from S2 in GF prime? There is a path, right? There is an edge SE. So E will also be there. So what about C? Is there a path from S to C?
No, no.
Are you sure?
S to C is no, ma'am. S to C,
See the yellow
There
part
is a
only.
path from S to E, E to F, and F to C, ma'am.
Yes. So see, we have a path from S to, so no. So the definition is we have to consider all those vertices which we have to just check from basically source vertex. So, all those vertices which have a path from source vertex. So for S to E there's a path, so E will be included. F will also be included because there's a path from S to F, namely S E E F. And C will also be included because there's a path from S to C, namely S E E F F C. So is there any other vertex such that there's a path from source vertex? No. So you'll see that these are the only three vertices such that there's a path from S to, there's a path from source vertex to, there's a path from source vertex to the, so this, there's a path from S, so this is little s, that is we are looking from path from source vertex. Okay, so S is this and S bar is the rest over vertices which are DA DT. So let's see if it is, so if it is the right answer. So we are saying that this is our cut S C E F. So what is the capacity of this cut? What is the capacity of this cut? If S is S C E F, what is the capacity of this cut? We are verifying the max flow minimum cut theorem. So we have found that this flow, this graph has maximum, this network has maximum flow of 28. So max flow min cut theorem says that there should be a cut with capacity 28. And the claim is that if we look at all the vertices S, all the vertices S such that there's a all the vertices U such that there's a path from source vertex to U in the residual graph. So we saw in this was the last residual graph, and we saw that S C E F are the only such vertices. So now if if this is, if the max min cut theorem is true, this capacity should also come out to be equal to the maximum flow, which is 28. So is it true? So what is the capacity of this cut? So for to find the capacity, we have to look at all the edges which are going from S to S bar. So what all edges are there from S to S bar in the original network?
SA,
SA, yes.
CD,
SA, CD, and
EF,
so EF.
sorry,
Uh,
F,
yes.
FT,
FT. Yes. CFT. Any other? So you're saying C.
backward edges.
Yeah. No, we don't need backward edges. For capacity, we just need the forward. We need just
Or
the edges from S to S bar. So what is CSA? Capacity of CSA is 10. Capacity of CCD is 8 and CFT is 10. So we see that capacity of this cut is also coming out to be 28. So this is indeed the minimum cut. So is this question clear? So this question was basically
Yes.
saying that given a network, we found out the maximum flow, and from the maximum flow we found out the minimum cut also. So are all these steps clear, that from a network how to find the maximum flow, and then from maximum flow how to find the minimum cut? Is it clear to everyone?
Yes, yes, ma'am. Yes.
Okay. Now let's look at the last question. Okay, so this is just the repeat. So first this one, let's see this. So we are given that if F is a flow for network G, we have to, what is the number of edges in the residual graph between U and V, and also we have to tell their direction. So if the flow value is strictly less than capacity of the UV, so suppose UV is a directed edge and UV is a directed edge in G, and flow value is strictly less than capacity, so in the residual graph how many edges will be there? This is also, yes. So in the residual graph how many edges will be there?
There will be two.
Two. And what so there will be two edges, and what will be the directions and weight?
Forward edges with the capacity minus flow.
Forward edge with the capacity as
Uh,
the difference,
Weight difference.
and backward edge
Backward with flow.
backward with flow. Good. Now if flow is equal to capacity, how many edges will be there?
One, one,
One.
Okay, so if flow is,
one and forward.
are you sure it will be a forward edge?
Yes, ma'am.
No. So
Backward.
backward edge, right, with the flow value, this will also be zero grade. So forward edge is the difference, but there is no difference, so there will be a backward edge with flow value UV, and weight will be FUV. And if flow is 0, then how many edges?
One forward edge.
One
One.
with forward. One with forward.
One with forward. With, and what will be the weight?
Capacity. With the weight is the capacity.
Weight is the capacity. Good. Okay. So now next question is this. So we are given that F is the maximum flow, GF is the residual flow, and S is the set of all vertices such that there is a path from S to U in the residual graph. Okay. So this was how we were finding the minimum cut. So if we were having F is the maximum flow and GF was the residual flow, we were looking at all the vertices in the original in the residual flow, such that this was our source vertex, and we were including all those vertices U if there's a path from S to U. So such U was included. Now first part is saying you have to show that if UV is an edge such that U belongs to S and V belongs to S bar, then question is the flow value equal to the capacity value? What do you think? So first of all, if you so S is a source vertex. If U belongs to S, what does that mean? By definition, what does that mean? If U belongs to S, S is this is little s and S is the capital S. This one is the capital S. So if U belongs to S, what do we mean? That we means that there is a in the this is residual, there is a path from S to U in a residual network. And if V belongs to S bar, that means there is no path from S to V. Okay, so we have this is the picture, and in there is no such path. Now you have to say that is FUV equal to CUV. So first of all, if there in a residual network, if there is a path from S to U and if there is no path from U to V, is it possible that UV is an edge in residual flow? Is this possible? Can you
No, it's not possible.
no? Why?
Because S to V, you have a path, then if we there is a path between U to V,
Yes.
then there will be a path from S to V also.
Yes. So
So,
UV
it,
is not an edge in residual flow. Correct. Because if UV is an edge in residual, UV is an edge, this will implies that V also belongs to S. That is, there will be a path which is not a con. So now if UV is not an edge in residual flow, that means, but UV was an edge in original graph. So if UV is not an edge in residual flow, that means there is no forward edge. And when is that possible? So since UV is not an edge in a residual flow, that means there is no forward edge. And when is that possible? That in residual flow we have no forward edges.
the question here is
Yes. Question is, I am asking, so we have so from this we have concluded that since U is an edge in GF, U is an UV is an edge in residual flow. That means UV if the UV is not, if UV is not an edge in residual flow, that means there is no forward edge. So can we say that F, since there is no forward edge in residual flow, then FUV has to be equal to CUV. So I am
yes,
saying
ma'am.
yes.
Yes, ma'am. And it has to be greater than zero.
Let's say because capacity we are all is like generally great look, so all the weights we take generally greater than zero. So let, yeah, so let's say it is zero.
Okay.
Yeah. So this statement is true then, right? So we have shown
Yes,
the
ma'am.
trueness of this statement, that if UV is an edge such that U belongs to S and V belongs to S bar, then FUV has to be equal to CUV. So is A part clear? Why is it true?
Yes, ma'am.
Now B part is saying, suppose UV is an edge but U belongs to S bar. That means there is no path from S to U in GF. But V belongs to S. That means there is a path from U to V in GF. So now can we say anything about FUV? So now we'll apply the same logic. Since there is a path from S to V, now UV was an original edge in G. Now since there is a path from S to V in residual network, but there is no path from S to U, that means VU is not an edge in the residual flow. And this can happen. So that means we have no backward edge. So that means we have no backward edge. And if there is no backward edge, what can we say about FUV? What is FUV?
There is no backward edge here means
Capacity.
from
You
V to U.
So see, I'm just saying that UV is an edge in G. UV is an edge in G.
Mm.
UV is an edge in G original network. Then we are looking at GF, residual flow. And we are saying that UV is an edge in G. So residual flow mein there are only two possibilities, that there will be a forward edge and there can be a backward edge. But due to this, since U is belonging to S bar and V is belonging to S, we see that there is no, that this possibility is not there, that if you, there is no backward edge in the residual flow. So when does that happen? So basically, first question, okay, let me phrase it like this. Suppose this was my UV edge in G with the direction U to V, and this is my flow value, and this is my capacity value. So in my residual graph, when will I have a backward edge? That is an edge going from V to U. When will this edge be there?
when flow is less than capacity.
No, no. If flow is less than capacity, then we have a forward edge with C minus S.
Okay, sorry. When flow is equal to capacity.
No, no. That was also when flow is equal to capacity, then there is no forward edge. If flow is equal to capacity, then there is no forward edge. But the question is when there is a backward edge. Backward edge, when do we draw a backward edge?
Is it similar to the first question, ma'am?
Yes, yes. It is similar to first question. So when do we draw the backward edge? If flow is greater than 0, right? If flow is
Great.
greater than
Yes.
0, only then we draw the backward edge. But if flow
Yes.
is 0, then there will be no backward edge, right?
Mm.
So we'll say, so the answer to second question will be FUV is 0. Because if flow value is 0, then there will be no backward edge. Is this clear?
Yes, yes.
So the in this the f of u comma v is equal to 0 means we have only the backward edge.
No, no. If FUV flow,
Um,
so see, so what were the two properties of residual flow? First of all, if flow is strictly less than capacity, then we have a forward edge. And if flow
yes,
is
ma'am.
strictly greater than 0, then we have a backward edge. But if flow is 0, so in all the examples that we did, if flow value was 0, then we were only drawing the forward edge. There was no backward edge in those directions, right?
Yes, ma'am. Yes, ma'am.
So that is the question, that in which scenario there will be no backward edges when the flow value will be 0.
So,
Okay. So this was all. So do you have any doubts in any of the problems today?
thank
No,
you.
ma'am. Clear.
Okay.
Thank you,
Then
ma'am.
I'll
Thank you, ma'am.
okay. Then I'll end the session.
Thank you, ma'am. Thank you.
Okay.